looking at the using reality capture to improve innovations as well as improving physical distancing on site in these times. I'll go over again quickly who I am. Sorry, Hunter Etherington, VDC Coordinator for Chandos Construction. Was architectural technologist by trade at NATE. I do believe that this the way I used our scanning and verification of dimensioning on site on this project really came from my experience working as subtrade. Not having all that accurate information to be able to validate until very late in the process was difficult as a subtrade. So bringing that experience really helped on this project. Who we are at Chandos. Chandos is a general contractor. We're started in Edmonton, Alberta. We have offices now in Vancouver, Kelowna, Edmonton, Red Deer, Calgary, Toronto, and Ottawa. We're medium-sized GC with about 500 million revenue in a year. We are completely employee-owned, and we have been so since our inception in 1980. One thing that we're very proud of is that we're a B Corp, which is a benefit corporation. That means we don't just do, we include social procurement within our projects, really benefiting the whole process, not just Chandos as a company. Here's a great picture of actually our VDC coordinator out in Vancouver working on projects with us. We generally work on design build, design bid build, and IPD projects are main scopes of contract types. We really focus on the IPD. Also, we do really great renovations, which we're going to focus on. We build in the civil, commercial, education, healthcare, hospitality, industrial, institutional, recreational, residential, special projects, and technology sectors. The project I'm going to be focusing on is the Queen Elizabeth II Planetarium in Edmonton. I'll show you a quick video on this.
We are standing just outside the Queen Elizabeth Planetarium. The City of Edmonton has been working on the restoration of this building, and today they are lowering the 8 panels of the dome and putting them in place. Queen Elizabeth Planetarium was the first opened public planetarium in all of Canada. It remained open until 1983. So the City of Edmonton really saw that as an opportunity to restore this building and make it a historical site for the future.
So you say, like the video showed, it was a heritage building built in 1960, closed since 1963, that we're renovating back to its original state, as well as adding a washroom. So the main 2 scopes of work that we focused on for reality capture were the interior projection dome for showing videos inside the planetarium itself, and then recladding of the exterior dome, installation and recladding of the exterior dome with a precast dome. So it's an overview of how the session is going to go. These are our main learning objectives. We're looking at how to capture the right data, sharing that data, validating that data, and then improving the install. So first, how to capture the right data. So our first problem was the interior dome replacement itself. So the existing dome was demolished before we decided to scan the building because we wanted to have those existing conditions 100% decided or understood. So we spoke with our supplier to understand what they needed. And one of the things they needed was the steel support angle. It was the left after demolition to hold and carry the weight of the new dome. So your interior subtrade, right here we have the difference between the original 1959 drawings and the drawings produced for this renovation. And that secure angle, you can kind of see, is in the same spot in both drawings, was needed to carry that new support angle. So understanding where we need to scan was important. So we need to make sure we captured that steel angle super accurately, even higher, with higher accuracy than what we compared or what we scanned the rest of the building. So always a huge important step when I'm planning out my scans is I take my drawings, whether in CAD or PDF, and I start overlaying where I want my scan locations. Because I want to know, I'm using the BLK 360 so I know what distance is accurate to. About 6 meters is wide. Make sure not to place my scans too far apart. Make sure I have the coverage always. So this is the original scan plan. It looked like it wouldn't take too many scans, so thought about 4. It's a very simple space. Like I said, using the AutoCAD planning is really easy. Once on site, our surveyor who was running the scan, using the tools from Recap on the iPad connected to the BLK 360, he understood that he had proper coverage with only 3 scans, made it a slightly faster process, and still had just as accurate information. So onto the exterior dome installation. We were concerned with scanning and getting accurate scans of a dome. There's plenty of space around the roof. It was just a fairly tall dome on top, so we had lots of space to work. Our subtrade on this project was Lafarge Precast. They requested as-built dimensions. Their original request was just the diameter of the diameter of the dome, as well as the height of the dome, just to confirm how their design was going to function. So to capture that, I once again threw it into CAD. And this is where it was a little tricky planning out this scan. As anyone who had worked with laser scan technology before, it's a line of sight technology. So scanning the inside of a box is easy because you got straight corners. But if you're scanning the outside of a circle, it takes a little bit more scans to get the actual coverage you want. So this is how I laid out the scans in CAD. Triggering that even was because we wanted the top of the dome. And so to get the top of the dome, you had to see the top of the dome. In CAD, I did a few plans to try to determine how I needed to capture that top of the dome. And working with our surveyor and our safety team, there was a little bit of concern on how to get that accurately measured. So we did, and safely as well. I left it up to our site team, our survey team, to work on a solution. And our surveyor found a great tripod with a large mast and kind of came up with a very unorthodox solution of placing the tripod on the edge of the dome and on a sawhorse to get up to that height. A little nerve-wracking, but it worked really well. So in the end, we ended up with about 12 scans around the outside, as well as the 4 to 5 ones above. Next, we're sharing data. So sharing data is important to communicate with your team, extracting that data and sharing that data. So interior communication. So like I was saying, the first you have to ask them how they can absorb the data or how they might want to see the data once you're sharing it with them. So this supplier, Astrotech, they're out of the United States. They did not have the capability to work with the scan data directly. They had basic CAD capability, so we had to work together to come up with a plan to share this data easily. And those were with tools we'll go over in a second. So first, we're talking about how they needed the information. So the first piece of information the supplier needed was how flat the existing support angles need to be. They couldn't have, as you know, in a lot of renovation projects, you can't have stuff like when stuff gets demolished, there's a tendency for things to get deflected. They were concerned that the existing steel would have been moved out of place from when it was demolished. So they needed to understand that it was flat enough to carry their structural tension ring to hold their dome. So to communicate that effectively, I used Bloom Cloud Engine, and I used the deviation reporting tool. So I'll come back to this a lot. I really love that deviation reporting tool. So first I created a plane that was parallel to the floor, and then I moved it to the average height of the underside of steel. I was able to run a deviation report to tell me how the steel angle deviates above and below that plane. So that's this light green plane you see here. That's up at the level of the steel angle. So once I did that, I created a deviation report. You can kind of see around the edge, the yellow and red and the green around the edge, and it's a little bit of blue there. That's showing how it deviated above and below that plane. And then on top of that, I gave the vertical dimensions from floor to underside of support rail for the supplier to understand exact and be comfortable with how those dimensions were decided. So I use the collaboration tools then within Bloom, which allowed me to upload this exact snapshot of scan to an interactive viewer on a browser. So that means that they didn't have to download any additional technology for them to view and be comfortable with how the data was understood and captured. It really benefited us in the long run that they were able to stay in the States and not come up for a visit just to take dimensions. The next piece of information they were looking for was radial deviation. They really wanted to know that their space on the existing rail or the existing steel angle for their tension ring. So unfortunately, the regular deviation tool wasn't working with the data we captured. There's definitely a slight regret I have that didn't take a scan that was a little bit higher in the interior dome, so we could see the interior edge of the steel angle. So instead, I created a cylinder in the center of the room with the minimum radius required by the supplier. I then exported this scan data to CAD, which I then was able to export or extract the radius from the scan data of the existing steel angle and compare it against the tension ring dimensions. I was able to then send that 2D CAD information straight to our supplier for them to verify themselves. So once again, not sending them the heavy gigs of scan data. It was just a cloud-based or CAD-based simplified geometry, so they understood what they were getting. For exterior communication, it was very similar. Lafarge did not have capability to use raw scan data as well. They did have access to AutoCAD, so we told them that I would be able to get them basically I'd just get them CAD data for the height of the dome and the diameter of the dome. So one thing about looking at the data extraction of this was just to compare it to the existing drawings. So these are the drawings in red here from the architect, in which we were able to just overlay straight into the 3D scan data to verify that if the design was accurate to what was as built. So as you can see, kind of on the bottom left of that screen, you can see the concrete actually goes past where the edge of the dome is. So this is why Lafarge was asking for that radius or the diameter of the dome, because it wasn't accurate to the drawings. And this is a great use of Bloom as well to overlay these 2D CAD data within the 3D scan data environment. So this is great to use. One thing we've used on many different renovations as well to verify that the 2D drawings match the existing conditions without the need for a lot of running around with the tape measure to check on dimensions. We can overlay the 2D CAD data over the scan directly without having to do a step of modeling just to verify on-site dimensions. This will reduce the amount of people on site that you need, because a lot of the touching common surfaces on site, because you don't have someone running around with the tape. So again, this time I used a different tool to get that radius at the bottom of the dome, because what I needed to do was understand where that bottom of the dome was. So instead of creating just a flat plane, what I did was I used a tool which is create a plane best fit to points. So I was able to select all the points around the edge of the dome, and then it created a plane that fit there, so then it lined up exactly with the bottom of the dome. And that's what I used to understand the diameter of that dome. So then I was able to export that radius to CAD. This allowed me to easily identify where that base of the dome was, and it was a good basis of communicating that design to Lafarge. Next, I needed to extract the height of the dome. And instead of just getting that center height, because of how I compared it to the 2D data before, I knew that the dome wasn't a perfect dome, so I wanted to collect more data. So within Bloom, I was able to create this grid of points. And actually, I can use the same deviation tool that I used from planes beforehand to use on these points. And this gave me what they call deviation spikes that I was able to then export to CAD to build out a basic CAD format of the dome. So as you can see there were the deviation spikes and the radius of the dome on the left. And then I connected them with best fit spline or fit to point splines in 3D to create that wireframe. And that was more simplified, but still had enough detail for Lafarge to accurately design their dome. So now validating the information. So what do you do when you get the information back from your subtrades? So first thing we got back was just a simple tension ring from the dome supplier. So it was simple enough that we had the information we needed, and we didn't have to overload the model. They didn't have to do extra work to create something that they didn't have already. It's really a kind of minimal viable product to confirm that we had the information we needed. So then we were able to send this to we were able to put that in the model. In red, you can see that's where the actual tension ring is. And these are 4 separate images that I sent to the supplier, so he's confident able to zoom in and understand how that aligned with the steel angle, and was able to confirm that he had the information he needed. So you can tell here's a closer snapshot of that red angle against the steel scan, or the scan of the steel angle. It's the same way I imported 2D CAD data. I could import the 3D CAD data. So this way I was able to position it and visually clash detect against the 3D scan without worrying converting my scan perfectly to CAD. So the interior report back. Once the supplier confirmed the support iron would work properly, they provided an accurate model of the dome for our future use. So this is a great way. I don't think before we did the 3D scan and communicated in the 3D space, we were going to be getting an accurate 3D model of the dome we were getting. All we were going to get were 2D shop drawings. So imagine trying to do the same thing we did with the scan, but validating just 2D shop drawings. There would have been way more questions, a lot more back and forth. It would have been a much more difficult procedure than just sharing it in the 3D environment. Next, after Lafarge got their 2D or their simple CAD data, they were able to use their to develop the 3D model around that wireframe and build something accurately. So they provided us the initial model of their ductile dome for us to review. Once again, it was lower detail, had an appropriate level of detail to verify design. We needed that inside face. So this is a very important note when working with subtrades is don't expect the final model right away to validate. Realize what's important to validate that information beforehand and look for that instead of trying to find the final 100% model. You don't need LD 500 models to just validate the information. This is more like an LD 300. So next, to review the data, I did the same thing, imported that CAD data into the scan that I had been using in Bloom. I already had the center point because I used that for creating the wireframe. So I just lined up the dome in the same spot to validate that they've designed it correctly. Next, I used a great tool, the great deviation tool I'd used previously, but this is one of my favorite uses of it. You can see that it's not just flat surfaces that the deviation tool can compare to. So it's comparing the dome, the scan of a spherical dome to the inside face of a spherical dome so we can understand how far away it was from that. In this instance, we needed the interior face of that new dome to be a minimum 100 mils away from the inside face of, or outside face of the existing dome to allow for 75 mils of insulation and a 25 mil airspace. So you can tell by this heat map, the red is where it's farthest away and the yellow is where it's closer, just to make sure our teams were comfortable with the information I was providing with them. There's a tool to actually point out the highest and lowest points of deviation. So we could tell by at the closest, it was 109 mils, and at the farthest away, it was 229 mils. So it was accurate to our site, or to our needs. I also uploaded it to that same cloud-based viewer for our site teams, so they didn't need me, or they didn't need to come to my desk to verify this data. They could view it from anywhere. We had people using the internet on site be able to view it, as well as the people on the different desks in the office view this data to make sure it was correct. And then at the end, once Lafarge and Chandos were comfortable that the dome was designed correctly, they sent us their final model, which had more detailed faces, as well as the overlaps for us to check for install, which turned out to really help. So speeding up install. So once we validated the interior dome was going to fit correctly on the existing structure, they shared their final model. We then used this to check for any further issues. It's typical in our projects for our VDC team to do constructability reviews between provided 3D models, mechanical versus structural, stuff like that. But I took the same approach, but compared the 3D model to the 3D scan data. I found that the existing duct, you can see on the left of the image, there's an existing duct that matches the inside face of the dome. So that duct actually was conflicting with, excuse me, with the existing ducting. So that way we had, we knew that and shared that with the team. And that duct was already set to be replaced, but was set to be replaced by the same size of duct. So finding this issue before that was replaced, they were able to easily change that duct to a more low-profile duct that still functioned the same to avoid the structure. If this would have happened on site, this is being installed by the subtrade out of the States, so they would have had delays, additional stays, maybe an additional trip depending on that person's scheduling, costing this project a lot more money, and would have been a lot more unsafe in these times for having people travel multiple times to our site. But with that information found, the install went perfectly. The installer was able to come from out of country, please install, no extra time or return trips, really benefiting the project. Next was verifying the install tolerances. So as I said previously, we had to make sure that the insulation was 75 mils thick, and we had a 25 mil airspace for this dome to fit properly. So the insulation was spray-on foam insulation. They were concerned about being high in some places, so we decided to scan again the exterior of this dome with the insulation in place. I was then able to use. We scanned the dome again and compared it against the final 3D model. We were looking for that 25 mil airspace between the insulation and the new dome. This image, you can see that some areas were out of tolerance. The blue areas, those were areas that didn't meet the minimum space required. So they didn't touch the inside of the dome, but they didn't have 25 mils of space. And the yellow and red areas, those were actually in conflict with the new dome, which would have caused issues even fitting it onto the building when it was on site. So I was able to share this information out to our project team so they could use these images of reference when they're up on top of the building. And then I also shared location information with our survey team because we had our scans survey controlled. So I was able to give our surveyor precise points to mark on the outside of this dome as to where it's high. So I gave him some outlines and some high points, and he was able to accurately tell the site team which parts need to be shaved down, and it really helped speed up that process. So once we had all the insulation confirmed that it would fit underneath the dome, this meant the day of install, there's no downtime for adjustments. All work could go ahead smoothly. There's 2 cranes, a large crew of people, and then there's no need for multiple crews to be there at the same time. In these times where we're concerned about physical distancing on site, it's a little difficult to get people in place and working on in scope, like when your scope is overlapped and you have two different groups of workers working in the same spot, it can be a little dangerous in these times. So we wouldn't have to worry about that at this point. But we have, so the concrete erectors didn't need to be interacting with any Chandos or other subtrade while they worked. Really went smoothly. We had media on site at the time. You saw the video beforehand. If there were any problems with this install, it could have looked very bad on us, but it went perfectly because we had our scan data verified. So here's just a review of what we've gone over so far. So keys to scanning renovation. You want to ask for exactly what information is needed. If you just go in, assuming you're going to capture everything that you need, you're going to miss things. I know because I've done this. This wasn't the first scanning project I've worked on. It takes time to go back. Always think of what you actually need. Plan site access with your project execution team, making sure you have the proper access at the right times. Like I say, if we went in too early, the interior dome would have still been there. It wouldn't have captured the data we needed. Layout proposed scans in CAD or PDF first. Planning is always a benefit. It allows you to understand the coverage you're going to get, and always overestimate. You have tools on site to make sure that you're capturing the right amount of data. So always overestimate the amount of scans you have because it's better to have more data than less. Next, keys to sharing data. Meet them where they are. Understand their needs. The amount of effort to get this data to where your suppliers can use them is worth it. They're trying to help you. You want to help them out as much as possible as well. So that's where the communication is key, understanding what they need and going back and forth to understand what digital information they need. Data validation. Understand the level of detail you need. For example, on the interior dome, we needed to know where that steel angle was and where that tension ring was. The tension ring was the most important piece. That's all we needed. On the outside, we just need those interior faces to check against the exterior face of the concrete. Communicate with them. Again, if you don't get what you need from them, talk to them. Make sure you have what you need, and communicate what issues you've had with the data they've given you if you have any issues. And keep an eye on how tools you have are being used. When I compared the 3D dome against the scan of the dome, I was able to see, I got that idea from looking at the Bloom website and seeing that they were working with the boat manufacturer to verify that their 3D model of their boat matched the boat they actually manufactured. So those were it was a hull shape matching a hull shape using a deviation map. So like, why can't I use a dome on this? It was a perfect use of seeing what's out there and seeing what other people are doing. Don't just live in a bubble. Come to like view conferences like this and understand what's happening in the industry. Speeding up install. So I call this VDC without BIM. So we do the clash detections, that type of thing, without having an actual original 3D model. We use the scan in place of that. Validate our install requirements. So once you validate the actual shop drawing, let's validate what information's there and that it works for our install. Then plan with your site teams. Ask them what their needs are at that point and make sure you're getting what you need. And benefits of scanning when physical distancing. So you can review site conditions from a distance. You can reduce the overlap of teams on site. And great for suppliers that come from a distance at this point. The more traveling someone has to do, the more risk is involved right now. So reducing those travel distances is really helpful. And that actually brings me to the end of my presentation. I don't have a final slide. Thanks, everyone.